Hey, we're live streaming. We'll start in a couple of minutes. You're Chloe? Hey, it's 8 o'clock. Today we're starting a new chapter, section 4.1a, on solving systems of linear equations by graphing. Okay, so here's a definition. So before starting, I'll just mention that we are going to be looking at two linear equations at the same time. And when two equations are analyzed together, we refer to that as a system of two linear equations. And so a solution to a system of two linear equations in the variables x and y is an ordered pair, x comma y in parentheses, that satisfies the conditions of both equations. So another way to describe a solution is in the next sentence. A solution to a system of two linear equations is a point on each line. Graphically, if you were to graph both of the lines in a system of two linear equations, a solution to a system of two linear equations is a point where the two lines intersect. And then a couple of terms to learn. A consistent system of two linear equations has at least one solution, or the lines intersect at least one point, if it's a consistent system. An inconsistent system of two linear equations has no solution. Okay, so I'm going to draw three pictures, each one involving the x and y axes. So the x-axis and the y-axis. Okay, so on the left, I'm going to draw a system of two linear equations, the graphs of those two equations that has one solution. So as long as the two lines intersect at exactly one point, then that's a good enough example. So here's one of the lines and another line. So in this picture, the two lines intersect at exactly one point. So whatever that ordered pair is of the intersection, that is the solution to that system. It's the one and only ordered pair solution for that system. So in general, if two lines have different slopes, as long as the slopes are different, there will be exactly one solution to that system, because two lines that have different slopes intersect at one and only one point. Okay, so that seems pretty straightforward. What about a system of two linear equations that has infinitely many solutions? So if you graph two straight lines and the number of intersections is infinite, then what has to happen, do you think? Well, a horizontal and a vertical line intersect at only one point. For example, the x-axis and the y-axis. Those are two straight lines, but they only intersect at one point. So if two lines have an infinite number of intersections, then they're the same line. Yeah. That's the only way it can happen if they're straight lines. So there's many ways that I could draw a line, but the idea here is that the two lines are the same line. So what I drew here is not really two different lines. I'm just intending to interpret that as one line, and the other line is exactly the same line. So the two lines intersect everywhere on that line. So there are infinitely many solutions to the system of two linear equations. So think of the background here, or what's behind this. We have two linear equations, and we're graphing them. In the first case, when we graph the two different lines with two different slopes, they will intersect at exactly one point. And that means the system has one solution in the form of the ordered pair. And then if the two lines are exactly the same, the system has infinitely many solutions. So the first two systems here are consistent because they each have at least one solution. Okay, so this one is consistent because there's exactly one solution. This one is also consistent. It has at least one solution, but there are infinitely many. It's still consistent. Hey, what about the system of two linear equations that has no solution? Graphically, that means that the two lines do not intersect. What kind of lines do not intersect? Yeah, parallel lines. So if we just draw two lines that are parallel, that just means they have the same slope but different y-intercepts. So those are supposed to be two parallel lines, so they never intersect. That means the system of those two linear equations has no solution because they do not intersect. And this kind of system is called inconsistent because there's no solution. Inconsistent. Yeah, we'll look at a few examples of systems of two linear equations, and we'll solve the systems by graphing. Okay, so we've learned how to graph lines. So let's graph these. I'll try to be careful. When the graphing is left to do by hand, then identifying the solution if the two lines intersect, well, it sort of depends on how well you graph. Okay, so for the top line, let's find a couple of ordered pairs for the top line. We can pick, let's see, let's pick x to be 0 to start with. And when x is 0, 4y equals 8, so y equals 2. So we have the ordered pair 0, 2. I don't really want to use the x-intercept because I get -8, and I don't want to get too far away from the origin. So I'm going to pick x to be, well, let's see, if I pick x to be 1, no, sorry, what was I thinking? Oh, I could use 1, but I'm going to switch that to 4 so that the division works out nicely. So if x is 4, I get -4 plus 4y equals 8, then add 4 to both sides. 4y equals 12, and so y equals 3. So the other ordered pair, 4, 3, is about right here. So this ordered pair is 0, 2. This ordered pair is 4, 3. And then draw a straight line through those points. Okay, let's find a couple of ordered pairs on the second line below. So this time just finding the x and y intercepts looks like the arithmetic will be easy. When x is 0, we're left with 4y equals -4, so the y coordinate is -1. So 0, -1 is point on the second line. And then if we find the x-intercept when y is 0, we're left with 2x equals -4, so x equals -2. And so we get the ordered pair -2, 0. And then draw a straight line through those 2 points. So what do you think the solution is? The solution is the point where the two lines intersect. Well, it looks like it could be, if my graph is reasonably accurate, it looks like it could be -3, 1. And we can test it if -3, 1 is the solution, but I don't think it is. Then we can replace, remember, a solution satisfies the conditions of both equations. So just looking at the top equation, if I replace x with -3, the negative of -3 is 3, and then plus 4 times 1. No, that's not going to work out. So as you can see, solving by graphing is precarious. So a little bit later, we're going to learn how to solve systems using algebraic methods instead of by graphing, and the algebraic methods are much better. So in this example, because I didn't graph very accurately, we didn't find the solution. So let's move on to the next example. Maybe this one will work out more nicely. Let's see if we can solve this system by graphing. Okay, what did you come up with for 2 ordered pairs for the top line? The line -3x minus 3y equals 6. So just looking at the top line, it looks like the x and y intercepts will work pretty nicely. So if I pick x to be 0, then we're left with -3y equals 6. Divide both sides by -3. I get 0, 2 for a point. 0, 2. And then if I pick y to be 0, I'm sorry, I really blew that. If x is 0, we're left with -3y equals 6. Divide by -3, I get 0, -2. So 0, -2 is the point that I want instead of 0, 2. And then when I pick y to be 0, I'm left with -3x equals 6. Divide by -3, I get -2, 0. So -2, 0. And if we draw a straight line through those 2 points. Okay, then for the bottom line, let's see. If I pick x to be 0, 3y equals 18 means y is 6. So we're getting a point off that's almost off the grid. But we'll go ahead and go with it. 0, 6. And then I don't want to pick y to be 0 because then I get -x equals 18. And so x is -18. That's clear over here somewhere. So let's pick a different number. If I pick x to be, say, -3, that will be a little more reasonable. Replace x with -3, I get the negative of -3, which is 3. Subtract 3 from both sides, I'm left with 3y equals 15. Then divide both sides by 3, I get y equals 5. That's a little better. So the ordered pair -3, 5 is about right there. Okay, so we draw a line through those 2 points. We see that there's one solution. But my graph, even though I sort of tried to be somewhat accurate, it's still a little fuzzy. It looks like maybe -4, 4. So I'll put that as a question mark. -4, 4. Well, if we were to test it in the top equation, -4, 4, let's see, -3 times -4 is 12. And then -3 times 4 is 12 minus 12. 0 equals 6. Well, that's not true. So my attempt at solving by graphing, it's my fault because I didn't graph accurately. So evidently we need a better method for solving if it's left up to us to graph, to solve by graphing. Okay, solving by graphing is not impossible, just if your graph is inaccurate, then it's hard to pin down exactly where the point of intersection is. So hopefully my failures will cause you to look forward to the algebraic methods. That's what we're getting to. Okay, on these next exercises, let's determine if the systems of equations are consistent or inconsistent. So we don't have to graph them to do that. All we have to do is what? We know how to write linear equations in slope-intercept form. So we can rewrite each of the equations in each of the systems in slope-intercept form. And then we can tell just by looking at the slope-intercept forms whether the systems have one solution, infinitely many solutions, or no solutions. Okay, so let's rewrite each of the 2 equations in the system on the left. Rewrite each of those in slope-intercept form. So 7x minus 9y equals -5. Let's start by writing -9y equals -7x minus 5, and then divide every term on both sides by -9, and we get y equals +7/9 x plus 5/9. Okay, then the bottom equation, let's solve the bottom equation for y. First, subtract 8x from both sides, so we get -2y equals -8x plus 4. And then divide every term on both sides by -2. And -2y divided by -2 is y. -8x divided by -2 is 4x. And 4 divided by -2 is -2. Okay, so this is the same 2 lines, just now the system is written, each of the equations in the system is written in slope-intercept form. So what kind of system is it? Is it consistent or inconsistent? Yeah, it's consistent. The 2 lines have different slopes. That means the 2 lines intersect at exactly 1 point. So we can say the system has one solution because the slopes are different. And if it has one solution, it's consistent. We don't know what the solution is, but we do know that there's exactly one solution. Okay, in the next system, well, the bottom equation is already in slope-intercept form, so that's kind of nice. And let's rewrite the top equation so that it's in slope-intercept form. So I'll do that above this line here, 7x minus 3y equals 8. So we subtract 7x from both sides. And then divide every term on both sides by negative 3. Negative 3y divided by negative 3 is y. Negative 7x divided by negative 3 is positive 7/3 x. 8 divided by negative 3 is negative 8/3, so we write minus 8/3. So we can view these two lines as the two lines in the system. So what do we say about this system? Yeah, they're the same line, so there are infinitely many solutions. So infinitely many solutions because the two lines are exactly the same. When you graph them, one line is on top of the other, so they intersect at every point. So we have infinitely many solutions. Infinitely many solutions. And what kind of system is it? It's consistent. All it takes is one solution for a consistent system. So infinitely many solutions means that it's consistent. In other words, we don't get any false information from a consistent system. Okay, the system of equations on the right, let's rewrite the top equation in slope-intercept form. All we have to do is subtract 6x from both sides. So we get y equals negative 6x minus 4 for the top equation. For the bottom equation, a couple of steps are needed. First, add 48x to both sides, so we get negative 8y equals 48x minus 16. Then divide every term on both sides by negative 8. Negative 8y divided by negative 8 is y. 48x divided by negative 8 is negative 6x. And negative 16 divided by negative 8 is positive 2. So rewriting the equations in slope-intercept form, we can now look at these two lines as the system of two linear equations. So just by looking, we can tell what's going on here. So how many solutions are there? How many? Yeah, 0 solutions, no solution. The two lines have the same slope, but different y-intercepts. So there's no solution. And this kind of system is inconsistent. So pretty soon, within a few days, it will make more sense why we're using the terms consistent and inconsistent. Okay, in the next exercise, determine which ordered pair, if any, is a solution to the system of linear equations. So here's our system of two linear equations. We can observe that this system has exactly one solution. If you were to rewrite the top equation in slope-intercept form, you can do that. We would have, first step, negative 8y equals negative 2x plus 6, and then divide every term on both sides by negative 8. Negative 8y divided by negative 8 is y. Negative 2x divided by negative 8 is positive 1/4 x. 6 divided by negative 8 is negative 6/8, or minus 3/4. Okay, so if you look at these two lines, y equals 1/4 x minus 3/4, and y equals 2/3 x plus 3, we know that there's exactly one ordered pair solution. So that one ordered pair, well, maybe it's in this list of 5, but it doesn't have to be there. I mean, it's possible that all 5 ordered pairs are not solutions. But since there's only one solution, at most one of those ordered pairs is the solution. Okay, so if we test for 0, remember what it means for an ordered pair to be a solution to a system? It means that the ordered pair satisfies the conditions of both equations. So if I just start in the top equation, replace x with 4 and y with 0, then I get 2 times 4 minus 8 times 0, or minus 0, equals 6. This means 8 equals 6. As soon as I get a false statement, then we don't have to test it in the other line. As soon as we get a false statement, we're done. So this one is not a solution to the system. Let's test the next point, 5 1/2. So we'll just start with the top equation again. Replace x with 5 and y with 1/2. So 2 times 5 is 10, minus 8 times 1/2 is minus 4. And 10 minus 4 is 6. Well, that's true, isn't it? Okay, but we're not done. We have to also, since it's true for the top equation, we have to check to see if it's also true for the bottom equation. Okay, so replace y with 1/2 and replace x with 5. So replace y with 1/2, and then 2/3 times 5 is 10/3, and 10/3 plus 3. Well, it's pretty obvious that this bottom equation is false, because on the right-hand side, we're adding two numbers, both of which are bigger than 1/2. So this is false in the second equation. So the ordered pair 5 1/2 is a point on the top line, but it's not a point on the bottom line, so it can't be a solution. Okay, well, 3 more ordered pairs to test. Do you get the idea of how to proceed? So let's test the last point. So in the top equation, 2 times negative 9, replace x with negative 9, is negative 18. And then minus 8 times negative 4 is minus negative 24 equals 6. This is simplifies a little bit to negative 18 plus 24 equals 6. Okay, that's true for the top equation, but we also have to test the bottom equation. So the bottom equation, y equals 2/3 x plus 3, replace x with negative 9, replace y with negative 3. So we get negative 3 equals 2/3 times negative 9 plus 3. Is that true? Do a little bit more arithmetic. 2/3 times negative 9 is just negative 6. And negative 3 equals negative 6 plus 3. That's true. And since negative 9, negative 3 is a point on both lines, and both lines and the two lines together have one point of intersection, then the ordered pair negative 9, negative 3 is the solution. So just to reiterate that, the ordered pair negative 9, negative 3 is the solution. It's a solution to that system of two equations. Okay, the next exercise is a little shorter. We just want to see if this ordered pair, negative 11, negative 9, is a solution to this system. Okay, so for the top equation, we'll start with the top equation. Replace x with the x coordinate negative 11. Replace y with the y coordinate. If we get an equation that's true, then we have to also test the second equation with that point. As soon as we get a false equation, we can stop and say that no, the ordered pair is not a solution. So replace x with negative 11. We have 2 times negative 11 minus 3 times negative 9. We want to know if that equals 5. 2 times negative 11 is negative 22. And then we're subtracting 3 times negative 9, so minus negative 27. And negative 22 minus negative 27 is the same as negative 2 plus 27. And this is true. Negative 22 plus 27 equals 5 is true. Okay, so now we have to test the bottom line. Replace x with negative 11, replace y with negative 9. So negative 3 times negative 11 plus 3 times negative 9. Does that equal negative 6? Negative 3 times negative 11 is positive 33. And then we're adding negative 27, so 33 plus negative 27 equals negative 6. So 33 plus negative 27, that's 33 minus 27. But 33 minus 27 is 6. 6 equals negative 6 is false. Okay, so negative 11, negative 9 is not a solution. So the answer is no. Okay, let's try another solve by graphing. So maybe I will luck out this time. So for the top equation, it looks like well, if I pick numbers that work out nicely in the arithmetic, but are not too far away from the origin. So let's see, if I pick x to be 6, then the y-coordinate is 6 over 2 minus 10, or 3 minus 10, which is negative 7. Still pretty far away. So I think I'm setting myself up again. So 6, negative 7. So I've already sealed my fate, I think. 6, negative 7. And then find another point. Man, this line is just pretty far away from the origin no matter what. So if I pick x to be 8, then 8 divided by 2 is 4, and 4 minus 10 is negative 6. So I'm just humiliating myself here. So there's the line. Okay, now let's graph the other line. This might not be as bad. So let's see, if I pick y to be 0, then negative 4x equals negative 8. Divide both sides by negative 4, x is 2. So that's not too bad, 2, 0. And another point. Let's see, how about x equals, say, negative 2. Let's see. No, I'm going to change my mind. X equals 4. So if x is 4, negative 4 times 4 is negative 16, minus y equals negative 8. Add 16 to both sides, I get negative y equals positive 8. And then divide both sides by negative 1, I get y equals negative 8. So the ordered pair 4, negative 8. So 1, 2, 3, 4, 5, 6, 7, 8. So it looks like the two lines intersect down here somewhere. We know they intersect, they have different slopes. So what do you think that ordered pair should be? Well, I can't say for sure. My graph is not really extremely accurate. Okay, so I came up empty again using the solving by graphing method. Okay, the last thing we'll do is I'll just show you an algebraic method called the substitution method. So this says solve the system by substitution or elimination. I'll pick the substitution method. So what you can do is you can solve one of the equations for one of the variables. It doesn't matter which variable you solve for. I'm just going to solve the top equation for y. Solve for y. So we add 2x to both sides, so I get 3y equals 2x plus 3. And then divide both sides by 3, I get y equals 2/3 x plus 1. And then in the other equation is the substitution step. In the other equation, I'm going to replace y with 2/3 x plus 1. So I'll get negative 4x plus 5 times 2/3 x plus 1 equals 1. Then we solve this equation for x. So there's a little bit of arithmetic involved. Negative 4x plus 5 times 2/3 x is plus 10/3 x. And then I have to remember to multiply 5 times 1, so plus 5 equals 1. And we have to combine like terms on the left-hand side, and we'll subtract 5 from both sides too. So negative 4x, with when I replace that with a term that has a denominator of 3, this will become negative 12x over 3. And 10/3 x is plus 10x over 3. And then subtract 5, we get 1 minus 5 is negative 4. And then negative 12x divided by 3 plus 10x divided by 3 is negative 2x divided by 3 equals negative 4. And then we multiply both sides by the reciprocal of negative 2/3. And we get x equals negative 4 over 1 times 3 over negative 2. And I get negative 12 divided by negative 2, which is positive 6. Okay, so x equals positive 6. That's the x coordinate of the solution. Then we can go back and use substitution again to find the y coordinate. Y equals 2/3 times x plus 1. This time we replace x with 6. So we get y equals 2/3 times 6 plus 1. 2/3 times 6 is 4. 4 plus 1 is 5. Okay, so this algebraic method shows us that the ordered pair 6 for x and 5 for y is the solution. Okay, that's all we have time for today. So on Monday, we'll also be in section 4.1, solving systems of linear equations, not only by substitution, but by a second method called elimination. Okay, but that's all for today.